हेलो डियर फ्रेंड्स, आप सभी का स्वागत है आपके अपने चैनल फिजिक्स परफॉर्म पर। आज क्लास 10th का मैग्नेटिक इफेक्ट ऑफ इलेक्ट्रिक करंट। चलिए स्टार्ट करते हैं। लेट्स गो।
Hans Christian Ørsted conducted an experiment to demonstrate that electricity produces a magnetic effect. The experiment is set up for you as you can see. Let's see what happens if we close the key to allow current to pass from south to north. The magnetic needle originally points north. However, when current passes through the wire from the south to the north, the needle deflects to the west. As you saw in Ørsted experiment, when an electric current passes through a conductor, a magnetic field is created around the conductor. This phenomenon is called as the magnetic effect of electricity. Let's analyze this magnetic effect further. You will observe that if you place the compass above the wire and allow current to pass from the south to the north, the compass needle deflects to the east. If you reverse the direction of the current in the wire, the direction of the deflection of the magnetic needle is reversed. The angle of deflection is directly proportional to the strength of the current through the wire. A magnetic field is the extent of space surrounding a magnet where the magnet's effect can be felt. Thus, it represents the region under the influence of the magnet, just as an electric field represents the region of electric influence. A magnetic field consists of a number of magnetic field lines, generally referred to as magnetic lines of force. Magnetic field lines represent the lines of action of the force acting on a unit north pole placed in the magnetic field. Magnetic field lines are closed continuous curves, never intersect each other, mutually repel each other, travel from the north to the south outside the magnet, and travel from the south to the north within the magnet. You can determine the direction of magnetic field lines due to a current-carrying conductor using Maxwell's right-hand grip rule. According to this rule, if you hold a conductor in your right hand with your fingers curled around it and your thumb stretched out as shown, then your thumb denotes the direction of the current in the conductor, and the direction of the curling of your fingers indicates the direction of the magnetic field lines due to the conductor. In the example shown, the current in the wire AB passes in the direction of the thumb, from end A to end B. The direction of the magnetic field due to the current in the wire is represented by the curl of the fingers, as shown. This rule is also called Maxwell's corkscrew rule. Consider a right-handed corkscrew kept parallel to a current-carrying conductor. On turning, if the screw advances in the direction of the current, then the direction of rotation of its head gives the direction of the magnetic field lines due to the conductor. Thus, magnetic field lines around a current-carrying conductor are in the form of concentric circles and can be either clockwise or counterclockwise depending on the direction of the current. Magnetic field lines vary with the shape and form of the conductor. Let's take a look at the magnetic field and field lines around. A straight conductor, a circular loop, and a solenoid. An experiment will help you understand how magnetic field is spread around the straight current-carrying conductor. To begin the experiment, we fix a white sheet on a cardboard, which is clamped to a stand. Next, we pass a thick copper wire connected to a battery and key through a hole at the center of the cardboard. Finally, some iron filings are sprinkled on the board and current is allowed to pass through the wire by switching the key on. You will observe that when the current flows through the wire, the iron filings arrange themselves in a concentric circular pattern. By placing a magnetic compass on any circular field line represented by the iron filings, you can also detect the direction of the magnetic field lines. The direction of the compass needle indicates the direction of the magnetic field. Further, if you change the direction of the current in the wire, you will observe that the direction of the compass needle is reversed. Thus, based on this experiment, you can conclude that a magnetic field around a straight current-carrying conductor consists of concentric circular field lines. The direction of the magnetic field lines depends on the direction of the current in the conductor. In general, magnetic field lines around the straight current-carrying conductor form concentric circles around every point on the conductor, with the center on the axis of the conductor. Lie in a plane that is perpendicular to the length of the conductor. Increase or decrease with an increase or decrease in the strength of the current respectively. Create a cylindrical magnetic field around the conductor. We can analyze the magnetic field of a current-carrying circular loop through another experiment. We begin by fixing a white sheet on a cardboard and clamping it on a stand. Next, we pass a thick copper wire through two holes on the cardboard so that it makes a curve and forms the shape of a loop. Then, we connect the ends of the loop to a battery and a key. Finally, we sprinkle some iron filings on the board and allow current to pass through the loop. When current passes through the loop, the iron filings arrange themselves in two sets of concentric circles on the cardboard. Further, if you place two compasses on each set of concentric circles, you will notice that the needles point in opposite directions. This shows that the magnetic field due to a current-carrying circular loop takes the form of two oppositely directed sets of concentric circles. Magnetic field lines around a current-carrying circular loop have the following properties. The lines are circular near the loop and tend to get elliptical away from it. They travel in the same direction within the area enclosed by the loop. They are parallel to each other near the center of the loop, indicating the uniformity of the magnetic field. They lie in a plane perpendicular to the plane of the loop at its center. They increase or decrease with an increase or decrease in the strength of the current respectively. These lines create a south pole at the face of the loop where the field lines enter the loop and the current in the loop is in a clockwise direction. They create a north pole at the opposite face of the loop, where the field lines leave the loop and the current in the loop is in a counterclockwise direction. A solenoid consists of an insulated conducting wire wound on a cylindrical tube made of plastic or cardboard. Thus, a solenoid consists of a number of circular loops. That is, it constitutes a coil. The length of a solenoid is greater than its diameter. When current passes through a solenoid, each loop in the solenoid behaves like a tiny bar magnet, with the south pole of one loop facing the north pole of its adjacent loop, and vice versa. Thus, a solenoid consists of a number of tiny magnets of equal strength. All the tiny magnets in the solenoid together behave like a bar magnet. The end of the coil, at which the current in the coil is in a clockwise direction, develops south polarity, while the other end, where the current in the coil is in a counterclockwise direction, develops north polarity. To analyze the magnetic field and field lines due to a current-carrying solenoid, here is an experiment. In this experiment, we fix a solenoid in a slit in a cardboard. We connect this solenoid to a battery and a key. Finally, we sprinkle iron filings on the cardboard and close the key to complete the circuit. When current passes through the solenoid, the iron filings arrange themselves in a pattern that represents the magnetic field lines due to the solenoid. These lines can be traced using compass needles. Magnetic field lines due to a solenoid are parallel to each other and to the axis of the solenoid within it. Travel from the south pole to the north pole within the magnet, and travel from the north pole to the south pole outside the magnet. The density of magnetic field lines indicates the intensity of a magnetic field measured in Newton per ampere meter or Tesla. The intensity of a magnetic field can be increased by increasing the strength of the current, increasing the number of turns in the solenoid, or inserting a soft iron core in the solenoid. Using electric current, you can create magnets out of metals like iron, nickel, and cobalt. Magnets created using electric current are called electromagnets. An electromagnet is a magnet made of a coil of insulated wire wound around a soft iron core. The iron core is magnetized when an electric current passes through the wire. In other words, an electromagnet is a solenoid with an iron core. Electromagnets are more useful than permanent bar magnet in the following ways. Electromagnets have a stronger magnetic field than permanent bar magnets. It is possible to reverse the polarity of electromagnets, but not in the case of permanent magnets. Electromagnets can be easily demagnetized by interrupting the current. However, it is difficult to demagnetize permanent magnets. In electromagnets, the intensity of the magnetic field can be easily varied. However, magnetic fields of permanent magnets are of fixed intensity. You can convert an electromagnet into a permanent magnet by using a steel core. A magnetic field exerts a force on the magnetic objects under its influence. Therefore, a current-carrying conductor kept in a uniform magnetic field experiences a force that tends to drive it away from the field. The direction of the force on a current-carrying conductor in a magnetic field can be determined using Fleming's left-hand rule. To understand this rule, stretch the forefinger, middle finger, and the thumb of your left hand, holding them at right angles to each other. If the forefinger gives the direction of the external magnetic field and the middle finger points in the direction of the current in the conductor, then the thumb gives the direction of the force on the conductor. An electric motor converts electrical energy into mechanical energy using the magnetic effect of electricity. You find electric motors in household appliances such as fans, refrigerators, washing machines, pool pumps, and floor vacuums. An electric motor is built on the principle that a current-carrying coil rotates when kept in a strong magnetic field as it experiences torque. An electric motor consists of 6 main parts. An armature that consists of laminated sheets of soft iron, through which passes a shaft. A coil, in the form of an insulated copper wire looped over the armature. A magnet that produces a strong and uniform magnetic field. A commutator, which is a metal ring split into two and is also referred to as split rings. This commutator is connected to the two ends of the coil. The shaft passes through the center of the commutator. 2 carbon brushes, tightly fixed to the 2 split rings connecting them electrically to the coil. A battery that provides electrical energy to the motor. Let's examine how an electric motor works. Consider a rectangular coil PQRS, placed horizontally between the north and south poles of a magnet and connected to a battery. The end of PQ part of the coil is connected to the battery through the split ring S1 and the brush B1. The end of RS part of the coil is connected to the battery through the split ring S2 and the brush B2. Initially, current is directed from P to Q in the arm PQ and from R to S in the arm RS. This arrangement is similar to that of a current-carrying conductor in a magnetic field. According to Fleming's left-hand rule, the force on PQ acts in an upward direction and on RS in a downward direction, forming a couple. The coil begins to rotate until its plane becomes vertical, that is, perpendicular to the direction of the magnetic field. Magnetic fields of the coil and the magnets become parallel to each other as the coil rotates by 90 degrees and the couple acting on the coil becomes zero. However, the coil rotates further through 180 degrees due to inertia. The plane of the coil becomes horizontal again. When the coil rotates by 180 degrees, the split rings also rotate along with the coil. Now, the split ring S1 connects end PQ of the coil to carbon brush B2. Similarly, S2 connects RS to B1. This reverses the current through the coil. The current now enters the coil through S2, passes along S, R, Q, P, and leaves the coil through S1. The torque acting on the coil causes PQ to go down and RS to go up. The torque acts on the coil until it rotates through 90 degrees. Further, it rotates through another 90 degree due to inertia and becomes horizontal again. On completing one full rotation, the split ring S1 connects PQ once again to carbon brush B1. Similarly, S2 connects RS to B2. Thus, as long as the coil is connected to a battery, it continues to rotate and convert electrical energy into mechanical energy. The power of an electric motor depends on the strength of the current through the coil, the number of turns in the coil, the area of cross-section of the coil, the strength of the magnetic field, and the lamination of the iron core. This lamination reduces energy losses. There is no potential difference between the ends of this coil of wire. How then does the bulb glow? A magnetic field gives rise to an electric current in a conductor due to electromagnetic induction. In this lesson, you will learn how electric current is induced due to a magnetic field. At the end of this lesson, you will be able to explain electromagnetic induction through Faraday's experiment, state Faraday's law of electromagnetic induction, use Faraday's law combined with Lenz's law to find the direction of a current, apply Fleming's right-hand rule to identify the direction of an induced current, demonstrate the working of electric generators and explain domestic circuits. You just observed that there was no electric cell to maintain a potential difference across the circuit. Yet, the bulb started glowing. When the wire is moved across a magnetic field, the free electrons in the wire experience a force that makes them move through the wire, inducing an electromotive force EMF, and thus an electric current in the wire. This process of generating an EMF in a conductor by moving the conductor through an external magnetic field is known as electromagnetic induction. When a conductor is moved in a magnetic field or kept in a fluctuating magnetic field, the magnetic flux linked with the conductor changes. This change in magnetic flux induces an EMF across the conductor. The EMF generated in this way is called an induced EMF, and the resulting current is called an induced current. The phenomenon of electromagnetic induction was first studied by Michael Faraday. Michael Faraday hypothesized that current induced in a coil is due to a changing magnetic field. To test this hypothesis, he conducted an experiment. You can observe this experiment to verify Faraday's law. To conduct Faraday's experiment, We will begin by winding an insulated wire over a hollow paper cylinder to make a coil. Next, we connect a galvanometer to the coil. Finally, we insert a powerful bar magnet in the cylinder with its south pole entering the coil first. We observe that when the magnet is moved in, the galvanometer needle deflects towards the left. When the magnet is moved out of the coil, the galvanometer needle deflects towards the right. If the magnet is not moved inside or outside the coil, meaning the magnet is stationary, the needle immediately returns to zero. The deflection of the needle, when the magnet is moved in or out, indicates that a current has been induced in the coil. Thus, an EMF is induced in the coil due to the movement of the magnet. Faraday's experiment confirmed that a moving magnetic field is necessary for electromagnetic induction. The direction of deflection of the galvanometer needle depends on which pole is inserted in the coil first. For example, in the experiment you saw, if the magnet is inserted with north pole first, the needle will deflect in the opposite direction as that of the previous case. In Faraday's experiment, you observed that a relative change in a magnetic field induces EMF in a conductor. The magnetic field can be changed in two ways: by relative motion between the coil and the magnet, as you saw in Faraday's experiment, or by winding two coils on the cylinder near each other, as shown. In the second case, one coil is connected to a battery with a key. This coil is called the primary coil. The other coil is connected to a galvanometer and is known as the secondary coil. When the key is pressed, a current passes through the primary coil. This current produces a magnetic field. As the magnetic field around the primary coil increases, the magnetic field associated with the secondary coil increases equally. The change in the magnetic field associated with the secondary coil induces EMF in the secondary coil. This EMF can be observed through the deflection of the needle in the galvanometer. The quantum and direction of EMF induced due to electromagnetic induction depends on 5 factors. Let's examine these factors one by one. The first factor is the direction of motion of the magnet in a coil. This determines the direction of the induced current. If you insert the magnet in the coil, the galvanometer needle deflects in a particular direction. When you move the magnet out, the needle deflects in the reverse direction. Thus, the direction of current gets reversed when the direction of motion of the magnet changes. The direction of the induced current in the coil also depends on the orientation of the magnet. If you move the magnet into the coil with its north pole first, rather than the south pole first, the direction of the induced current in the coil is reversed. The speed of motion of the magnet through a coil determines the strength of the induced current. Thus, if you increase the speed of the motion of the magnet, the EMF generated increases, and vice versa. The strength of the magnet is another important factor. The quantum of EMF induced in a coil is proportional to the strength of the magnet. The stronger the magnet, the higher the induced EMF, and thus increased induced current in the coil. Finally, the number of turns in the coil also affects the induced EMF. Using a coil with a greater number of turns increases the induced EMF. Based on his experiments, Faraday postulated a law on electromagnetic induction. Faraday's law states that the induced electromotive force E in any closed circuit is directly proportional to the rate of change of the magnetic flux through the circuit. You can determine the direction of the current induced when a conductor moves in a magnetic field using Fleming's right-hand rule. This rule is also known as the generator rule. To use Fleming's right-hand rule, stretch the thumb, the index finger and the middle finger of your right hand so that they are at right angles to each other as shown. If the index finger points in the direction of the magnetic field and the thumb indicates the direction of the motion of the conductor, then the middle finger indicates the direction of the induced current in the conductor. Consider a conductor AB connected to a galvanometer placed in a magnetic field. The direction of the magnetic field is from the North Pole to the South Pole. When you move the conductor up, the galvanometer needle deflects to the right. This rightward deflection indicates the direction of the current in the conductor from end A to end B. If you move the conductor downwards in the magnetic field, the galvanometer needle deflects to the left. This indicates the direction of the current in the conductor from B to A. Thus, you can see that the direction of the magnetic field, the movement of the conductor and the induced current are at right angles to each other. Electric generators are based on the principle of electromagnetic induction. Generators are used to generate electricity in power plants for transmission and distribution of electricity over power lines, and to produce electric power required for aircrafts, ships, and trains. Dynamos used in automobiles are similar to generators, but they produce relatively less power. There are two types of electric generators: AC generators and DC generators. An AC generator is made up of four major components: an armature consisting of a laminated soft iron core with copper windings with a large number of turns, two slip rings made of gunmetal, which are connected to the two ends of a coil and rotate with it, brushes to provide electrical contact between the external load and slip rings, and a powerful horseshoe magnet or an electromagnet. Now let's examine how a generator works. The rotation of an armature, PQRS, between the magnetic poles results in a change in the magnetic flux linked to the coil. This induces a current through the armature. Here is a step-by-step account of how the current is induced. Initially, the coil is vertical with PQ on top and RS at the bottom. This coil is rotated clockwise so that PQ goes down. As the coil rotates through 90 degrees, it becomes horizontal. At this stage, the change in flux with respect to the initial position is maximum. Hence, the current rises from zero to maximum. The direction of current through each arm can be found using Fleming's right-hand rule. The current flows from brush B1 to brush B2. On rotating further by 90 degrees, the coil becomes vertical again. But now, PQ is at the bottom and RS is at the top. The change in flux with respect to the initial position is zero. Hence, the current falls from its maximum in the same direction and becomes zero. Rotating the coil by another 90 degrees causes the current to increase in the opposite direction. Now the coil has rotated through 270 degrees from its initial position. Now, the current flows from B2 to B1. On turning further by 90 degrees, the coil completes one rotation of 360 degrees. The change in flux with respect to the initial position is zero at this point. Hence, the current falls in the same direction and becomes zero. Thus, the current rises and falls for every 180 degrees of rotation of the coil in opposite directions alternately. The faster the coil turns, the greater the frequency of the current produced by the generator. In an AC generator, the induced current changes its direction periodically and is therefore called alternating current. An AC voltage is continually changing between positive and negative. The rate of change in the direction of the current is called the frequency of the alternating current. It is measured in hertz, that is, the number of cycles per second. The increase in value from 0 to the positive maximum, then the decrease back to 0, then the further increase to the negative maximum, and the decrease back to 0 is counted as one complete cycle. Like an AC generator, a DC generator also works on the principle of electromagnetic induction. However, a DC generator produces direct current and is commonly used in small-scale power generation devices such as a dynamo. A DC generator is equipped with a commutator, which is a pair of split rings, in a position similar to that of slip rings in an AC generator. A commutator helps in keeping the polarity of the brushes the same to ensure unidirectional current. The other major components of a DC generator are similar to that in an AC generator. A DC generator that contains a loop generates a pulsating DC current. To produce a more stable output, a coil with more turns is typically used. In a DC generator, when the coil rotates through 90 degrees, the change in magnetic flux induces an electromotive force of maximum strength. This current flows through the split rings to the brushes. When the coil is rotated further at 180 degrees, the electromotive force becomes zero. At this point, the contact between the commutator and the brushes is reversed. The first brush now comes into contact with the second segment, while the other brush comes into contact with the first segment of the commutator. This keeps the current going in one direction. Most of the power plants in the world produce high-frequency alternating current that is supplied to industrial and household consumers through power grids. Electrical components and wires fitted in a household to supply electricity to various appliances form a domestic electric circuit. Let's see how electricity is distributed through domestic electric circuits. A network of overhead or underground cables brings power to our homes. Domestic electric circuits are connected to this network through mains supply cables, commonly known as mains. The mains supply cable has two wires. The first wire, usually in a red insulation cover, is called a live or positive wire. The second wire, insulated in black, is called a neutral or negative wire. Electric current enters a domestic electric circuit through the live wire. The neutral wire provides the return path for the current out of the circuit. These wires pass through the main fuse in a meter board. A main switch connects these wires to the line wires in the house. Line wires supply electricity to all circuits within the household. Separate circuits may be used for power lines supplying 15 ampere and 5 ampere current. This is to provide for varied current requirements of appliances. Appliances with higher power ratings, such as air coolers and geysers, require a 15 ampere supply. On the other hand, electrical fittings such as bulbs and fans run on 5 ampere supply. Domestic electric circuits also have earth wires used as a safety measure against any leakage of current. In case of power leakage, appliances with metallic bodies such as electric irons and water geysers may convey excess current to a human body in contact. This can result in an electric shock and may, at times, also prove fatal. Connecting the metallic bodies of these appliances to earth wire ensures that any current leakages are conveyed to the earth. Hence, earth wires save users from severe electric shocks. Earth wires are generally insulated in green color. An electric fuse is an important component of all domestic circuits. An electric fuse is a safety device used to protect an electric circuit against excessive current. If your electrical appliances receive very strong current, they could get damaged and stop functioning. To prevent damage from fluctuations in the current,